In this video, we are going to continue with Ohm's law, Kirchhoff current law, and Kirchhoff's voltage law. So we define a few things, a few terms that we use, and we also define KVL and KCL. So Kirchhoff current law is defined as the sum of all the current that enter a node equal to the sum of the current that leave a node. Now, so let's review what we did. Kirchhoff's current law. Okay, sum of current into a node equals sum of current out of that node. Okay, so we gave this example where we have a node and we have current. So let's say we have this scenario. Okay, so let's say this is I1, this is I2, I3, this is I4, and the node is that. So that's the node. Okay, so for this node, what do we have? We have the current that are flowing to the node is I1 plus I3, and the current that are flowing out of that node are I2 and I4. So we have I1 plus I3 minus I2 minus I4 equal to 0, and which is I1 minus I2 plus I3 minus I4 equal to 0. So from this definition also we say that the algebraic sum, okay, the algebraic sum of current into a node is 0. So these definitions are equivalent. Okay, so now we say algebraic sum because of the sign that we have in here. So that was for KCL. Now what about KVL? So Kirchhoff's voltage law. Okay, so before we define Kirchhoff's voltage law, I'd like to define what we call a loop, right? So we did talk about loop also in one of our previous videos. So loop closed path. Okay, so A loop, okay, is a contiguous sequence of branches, um, of branches, okay, which begins and ends on the same node. And okay, so we have to emphasize on this. And touches, I know other node more than once. Touches no other node more than once. Okay. All right. So then we did say branch. So what is a branch? Right. So now what is a branch? Okay. So a branch. All right. So what is a branch? Okay. So a branch, okay, is a path that connects two nodes. Okay. Two nodes. Okay. So then, if you recall from one of our previous videos, we define essential node and simple node. Okay. So let me give you an example here. So example. Okay. So let's say we have this network. We have this voltage source, I call the VS1, and have R1, I have R2. Okay, so let me bring this down. Let's make it a little bigger so I can define branches and define nodes and all the terms in here. So, and then let's say this is R3 that connect to another voltage source. Keep it simple. Okay, and then we have a resistor. So let's say R4. Okay, so let's say that is R4, and I connect to the side of the power supply, and we have a current source, and let's say we have R5. Okay, so let's talk about the node, right? So let's define essential node. So essential node, right? We say two or more element meet, more element adjoin. Okay, so that is an essential node. This is an essential node. This is an essential node. This is an essential node. Okay, so we have four essential node. Okay. So as we trace, okay. So as we trace, okay. So as we trace a closed path, so we trace closed path, okay. A voltage will appear, okay, either as a rise, either as a rise or a drop in the tracing path. Tracing direction, if you like. Let me give you an example. So let's assume we have this VS1. I'll call this R1, R2, R3, R4. So let's put R4 and VS2, for example. Okay, so we have this loops. So this is a loop. I call it loop 1. This also is a loop. I call it L2. And this is a loop also. I call it L3. So what do we do in order to write the KVL equations? Okay, so what I'm going to do, we have polarity for voltages. We need to assign polarity to all the elements. So let's say this is VR1 and I'll call this VR2. Okay, so let me reload this correctly. So it's not clouded. So this is R4, so we called it. So I can have, right, we arbitrarily assign polarities. So V R4, and for this one, we can call it V R3. So we have polarity for all the element. So let's write KVL equation. Okay, so let's do it for loop 1. Okay, so for loop 1, we are going to trace a cross path starting from this node. Okay, so I'm going to start from that node, so and move upward. So in that case, as we move across the minus polarity of the voltage source first, So that will be minus vs1 plus vr2 r1, because we cross the plus polarity, plus vr2, right, because we cross, oh, I'm doing loop 1, so plus vr3, and I come back to that same node, so that is equal to 0. Now let's do loop 2. Okay, for loop 2, what do? We'll start from the bottom node and then we'll move upward, right? So I'm gonna move upward. So what does that give me? So I have minus v vr3, because I cross the minus polarity of r3, then plus vr2, because that's the polarity that I cross there, minus vr4, and then minus vs2, that is equals to 0. Okay, so now if I take the outer loop, right, if I take this loop, okay, starting still from the bottom, I will have, starting from that node, I'll have minus vs1, then plus vr1 plus vr2. Now resistor 4 minus vr4 minus vs2, and that is equal to 0, right? So, and those are the loops, right? So this would be for loop 2, and this is for loop 3. Okay, so the loop equations, right, these are the loop equations that we could get out of this network. So what are the practical considerations when we write KVL, right? So let me write it down here. So practical consideration on KVL. So now, so for any circuit, with n essential node and b branches, so b so essential branches. I'm gonna talk about this in a minute. Okay, so we can derive only b minus n minus 1 independent equations. Okay, so from so for this network that I have in here, right, you might notice later on, right, when we apply this particular considerations, that this is not really needed, right, but it's a valid loop equation, but to get the minimum set of equations to find the voltages and the current, right, the first two are well enough, but you can write as many as you want, and then you're gonna end up with, we're gonna find out that we don't really need all of them. So when you write to write KVL equations, right, we wanted to make sure that we don't end up with too many equations that's needed, right? So in order to do that, we had to stick with the fact that if I had n essential node and b essential branches, then b minus n minus 1 equations are going to be the number of independent voltage equation, right? Independent, let me say, voltage equations. Okay, and I'm gonna make sure that all this are crystal clear. Okay, so and now, so element connected to the same node are subject to the same voltage, right? So element connected to the same node are subject to the same voltage. Okay, so that meant, right, no need to apply KVL. Okay, we're going to do examples to make sure that all this are, crystal clear. Okay, and then when two or more elements are subject to the same voltage, they are said to be connected in parallel, right? So when two or more elements are subject to the same voltage, they are said to be in parallel. Okay, and to be connected in parallel, right? To be, if you like, be connected in parallel. Okay, so now okay, so when two or more elements are said to be connected in series, connected in series. Okay, so if they carry the same current, Okay, and so let me put some space here to elaborate. Now, so let's say that I have this where I have this is a node, and then I have this component, call it C1. I have this component I call C2. I have this component that I call C3. And the voltage across them is V. All right. So C1, C2, C3, right, share the same node, right? This is a node, and this node. Okay. So share the same node. So this implies that they are in parallel. Okay. Now, when I take this component, C1, C2, C3, for example, and the current I is the same current, and that's flowing through this component. So C1, C2, and C3, okay, carry the same current. An example to solve, to give an illustration on how we can use all this. So I'm gonna give you this example. So because we are going to have a lot of variables, I'm gonna make this really big so that so then we can clearly see the variables. Okay, so this is 2, 3, 4, 5. So let me put R4 here and R5 here. Okay, so now this is the network. Let's say this is VS. Let me call it VS. Okay, so VS, I'm gonna give, so to apply KVL and KCL, we give reference direction and polarity to voltage and current. Okay, so step 1, assign reference direction to current in each branch. Okay, assign voltage polarity assign polarity to voltage across each component. Assign a polarity. right? It's a reference polarity, right? Assign a reference. So let me write good sentence here. So assign a reference direction, assign a reference polarity to the voltage across each element. Okay, so that's what I'm going to do. So I'm gonna have to assign, so let's say this is current IS, this is current I1, the current through R4 is I4, I3, I5, I2. Okay, so then I'm going to assign voltage polarity. So call this V1, call this V2, call this, oh no, this is V4, cause R4, so V5, V3, V2. Okay, so we have polarity assigned to voltage voltage across each component. Now, so in step 2, so identify the essential node and essential branches. Okay, so essential branches are the branches for the current. So we have IS, I1, I2, I3, I4, and I5. So this implies that we have 1, 2, 3, 4, 5, 6 essential branches. Okay, so what are the essential nodes? Essential nodes are at the point where we have three or more element connected to. So let's say this, we use a different color. So let's say this is one of them, so I call it A. So then I'll call this one, we have 3 elements that meet there. So we have essential node B. We have at least 3 elements that meet here as well. So we have C, and then we have here we have D. Okay, so here we have 4 essential node. Okay, so the number of independent voltage equations, the number of independent voltage equations, right, for the circuit will be is okay, the number of branches, which is 6, minus the number of essential nodes, which is 4 minus 1. We wrote this equation above, so 6 minus 3, which is 3. So we have 3 independent voltage equations. Okay, so now let's find the loops. So that means we only need 3 loop equation, right? So only need 3 loop equations. Okay, so I will identify this as my first loop. So loop 1, this as my second loop, call this loop 2, and this as my third loop, because I only need 3. Okay, so let's write loop 1 equation. So for loop 1, we are going to start with node C. Okay, start at node C. Okay, so when we start from node C and moving in the direction of the loop, right? So what do we have? We come across the negative polarity of Vs, so negative Vs, and then we have plus V1. We come across the plus polarity of V1 first, then plus V2, come across the plus polarity of V2 next, and then we reach back C, so that we close the loop, that is 0. Now loop, so L2 equation. Okay, so for L2, start from node A and moving in the direction that I indicated there. So we come across R4, and the polarity of the voltage there will be V4. It's plus, so plus V4, and then minus V3, and minus V1, that also equals 0, right? Because we only have those 3 elements in that loop. So now let's do loop 3 equations. Okay, for loop 3 equations, what do? I'll start from C, then I'm going to move right in the direction. I'm gonna move clockwise. So I have negative V2, right? I come across the negative polarity of that voltage first, so negative V2 plus V3 and plus V5, and then come back to that node C, so equal to 0. So now I have my node, my KVL equations. Okay, now these are the KVL equations. So KVL equations. Now I'm going to do KCL equations. So for KCL equations, if you like, I'm gonna move this down slightly. I'm gonna move this down slightly. Move it down slightly, right there. Okay, so we have KVL equation. Now let's write the KCL equations. So what are the essential nodes, right? So we have node A first. So KCL at node A. Okay, so for KCL equations, let me indicate this first. So we have 1, 2, 3, 4. So we have 4 essential node. Okay, so this implies that we have 4 minus 1 equations to write, right? So because one of the nodes, one of the essential nodes, one of the essential nodes is used as reference node. Okay, so that means now we end up with so we have 3 equations. So I'm gonna use, so we are going to use node C as the reference node. Okay, so that means we're going to write KCL. So write KCL at node A, B, and D. A, B, and D. Okay, so KCL at node A. So let's try KCL at node A. So at node A, what do we have? We have the current living down node will be IS plus I1 plus I4, and then we have no current coming to that node, so that is equal to 0. Now KCL at node B. To make some space, so I'm gonna do it like that. So KCL at node B. So at node B, we have current I1 that comes to that node. So I1 is coming to that node, and we have I3 and I2 that are leaving that node. So I2 plus I3. Okay, so that means we have I1 minus I2 minus I3 equal to 0. So the last one at node D, so KCL at node D. So at node D, we have I4 that's coming to that node. So I4 and I3, that's I3, and then I5 is leaving that node, equal to I5. So it's I4 plus I3 minus I5 equal to 0. So these are the equations. Okay, so those are my node equations. So now when we look at, so now let's write Ohm's law. So I'm gonna copy this diagram down there, and I'm going to write Ohm's law. Make some space. So I'm gonna make it smaller to make it fit here. Okay, so now we know that for resistance R1, so here we have Ohm's law. So let's do it for resistance R1. We have current. Okay, so we have R1. We have current I1 that's going to R1. Right. So we have I1, and the voltage across that is V1. So when we write Ohm's law here, V1 is equal to what? R1 I1. So following the passive sign convention, the current is flowing from plus to minus. So that is V1. Now, resistance R2. So for R2, okay, so the current, we have I2 that's flowing through R2, and the voltage is V2. Voltage across it is labeled as V2, and this is R2. So V R2 will be equal to R2 I2, right? Following the passing sign convention still. So what about resistance R3? So for R3, we have R3, and we have I3, and the voltage across it is V3. So when we write Ohm's law here, V3 will be R3 I3, because the current is from plus to minus. So we have that. Now let's talk about resistance R4. So R4, we have the current I4, that is so this is R4, so the current, this is I4, and the voltage across that is V4. So the current is also flowing from plus to minus, so V4 is R4 I4. And the very last one, which is R5, so we have R5, so R5, and the current is flowing from plus to minus I5, and the voltage is V5. So passive sign convention, V5 equal to R5 I5. Okay, so putting it all together now, we have element relationship. Okay, so what do we have? We have V1 equal to R1 I1, V2 equal to R2 V2, V3 equal to R3 A3, and V4 equal to R4 I4, and at last V5 equal to R5 I5. Now let's write the KCL equations. So KCL equations. So KCL equations, what do we have? We have a node A. We have I0 plus I1 plus I4 equals 0. I call it IS plus I1 plus I4 equal to 0. Then at the node B, So at node B, we have I1 minus I2 minus I3 equals 0. And at node D, at node D, we have I4 plus I3 minus I5 equal to 0. Okay, so we notice that if you write the equations, the node equation at node C, that will be redundant, right? Because we only need 3. Okay, so now we do KVL equations. Okay, so KVL equations. We wrote the KVL equations. Those are the first one we wrote. So minus, I'm just gonna copy this down there for the sake of time. Okay, so those are our KVL equations. Okay, so we kind of put all this together. So what are the variables that we have here? We have, so with the variables, we have IS, okay, I1, I2, I3, I4, I5, and then we have V1, V2, V3, V4, V5. Okay, so these equations are going to lead us to solve for all this variables. Okay, so with the KVL and the KCL equation, when we substitute V1, V2, V3, and V4 in these equations, then we are going to solve for the voltages, solve for the current, and once we know the current, then we can find the voltages. So we are going to do an example with numbers next. Okay, so next we are going to do a few examples. Okay, so next we are going to solve a few problems. Okay, so please don't forget to subscribe as we add videos, and then you receive notifications. Thank you.